Good morning, everyone. My name is Prashant. I am from CSCB 7th semester. Today, I am going to give a tech talk about diagnosing autism spectrum disorder using ML techniques. Okay, so diagnosing autism spectrum disorder using ML techniques. This presentation explores the application of machine learning techniques in diagnosing autism spectrum disorder. ASD is a complex neurodevelopmental condition that affects communication, social interaction, and behavior. Early and accurate diagnosis is essential for effective intervention. Traditional diagnostic methods are often subjective, time consuming, and limited by clinical expertise. Machine learning offers promising solutions by identifying patterns in large datasets and aiding in objective, fast, and scalable diagnosis. We will use various ML approaches, datasets used, feature extraction methods, and real world implications of ML assisted ASD diagnosis. Now, coming to understanding autism spectrum disorder. ASD is a lifelong developmental condition marked by challenges in communication, behavior, and social interaction. It manifests in a variety of forms and severities, hence the term spectrum. The diagnosis typically involves behavioral assessments and clinical observations. However, due to its complexity, ASD is often diagnosed later in childhood, missing the critical early intervention period. Symptoms vary widely, making early detection difficult. Therefore, automated tests use machine learning that can help capture subtle patterns and provide support for clinical decision making, ultimately contributing to improved care and outcomes. So, why use machine learning for ASD diagnosis? Machine learning can enhance ASD diagnosis by offering faster, data driven, and more consistent assessments. It identifies complex, nonlinear patterns in large datasets that may be missed by humans. ML techniques can also reduce human error, overcome subjective biases in clinical evaluations, and assist under resourced areas lacking autism specialists. Additionally, ML can integrate data from various sources like behavior metrics, medical imaging, and genetic information to improve diagnostic accuracy. These advantages position ML as a complementary tool to existing diagnosis processes, aiding clinicians in reaching more timely and accurate diagnosis for children with ASD. So, let us look at the commonly used datasets. To train ML models for ASD diagnosis, researchers use a range of publicly available datasets. And these examples include the Autism Brain Imaging Data Exchange ABIDE, which provides MRI and functional MRI scans, and UCI's ASD screening dataset with behavioral test results. These datasets include features such as age, gender, screening scores, and sometimes brain imaging or EEG signals. Data quality, diversity, and labeling accuracy are vital for model reliability. Combining behavioral, genetic, and neurological data increases robustness. The pre-processing of these datasets, including handling missing values and normalizing inputs, is critical for the model training success. So, what are the key features of model training? Selecting meaningful features is crucial in building accurate ML models. For ASD, features may include questionnaire responses like MChat, eye tracking, speech patterns, motor activity, and brain imaging data. Behavioral metrics such as social response or communication scores are often strong indicators. In some cases, machine learning algorithms identify novel predictive features that clinicians may overlook. Feature engineering and dimensionality reduced techniques like PCA can enhance model performance. By choosing relevant and discriminative features, ML models can effectively differentiate between ASD and non ASD individuals, thus improving the diagnosis of the ASD and improving the quality and its reliability. Machine learning techniques employed. Now let us look at the different types of techniques that are employed, that are used. A variety of ML models have been employed in ASD diagnosis, including decision trees, support vectors or SVMs, key nearest neighbors KNN, and random forests. Deep learning models like convolutional neural networks CNNs are used especially when working with imaging data. Ensemble methods often combine multiple algorithms for improved performance. These techniques are trained on labeled datasets and evaluated based on metrics like accuracy, precision, recall, and F1 score. The choice of model depends on data type, size, and structure. Each algorithm has trade offs between interoperability, interpretability, speed, and predictive power in a clinical context. So, how deep learning is used in ASD diagnosis. Now let us take a look at that. Deep learning models, especially CNNs and recurrent neural networks RNNs, have shown great promise in ASD diagnosis. CNNs are effectively with imaging data, capturing spatial hierarchies in brain scans. RNNs include LSTM networks, work well with sequential data like speech or eye movement tracking. Deep learning automatically extracts features, reducing the need for manual selection. However, it requires large datasets and significant computing resources. Despite being harder to interpret, these models often outperform traditional ML in accuracy. They offer a scalable approach to ASD detection, especially when detected into telehealth platforms or mobile diagnostic tools. Now, let us look at the evaluation metrics. Accurate evaluation of ML models is essential. Common metrics used include accuracy, precision, recall, specificity, and F1 score. In ASD diagnosis, sensitivity, true positive rate, is especially important to ensure early detection. ROC AUC scores are used for comparing classifiers. Confusion matrices offer insight into classification errors. Cross validation ensures models generalize well across diverse populations. Overfitting is a key concern, particularly with small datasets. A high performing model must balance sensitivity and specificity to avoid both false negatives and false positives, ensuring individuals who need intervention are correctly identified and treated early. Now, what are the challenges in ML based ASD diagnosis? Despite its potential, ML in ASD faces several challenges. Data security and quality, especially for early childhood kids, limit model robustness. Many datasets lack diversity, reducing generalizability across populations. Labeling bias and inconsistency in diagnostic criteria also affect outcomes. Interpretability remains a concern, particularly in clinical settings, where transparency is vital. Ethical issues such as data privacy and consent must be managed carefully. Additionally, reliance on ML models without proper clinical oversight could lead to misdiagnosis. Addressing these limitations is essential to make ML tools more reliable and trustworthy in healthcare environments. Ethical and social considerations. Implementing ML in healthcare requires addressing ethical considerations like data privacy, bias, and informed consent. Patient data, especially involving children, must be anonymized and securely stored. Models trained on non diverse datasets may perpetuate bias and inequity in diagnosis. Transparency in how predictions are made is necessary for clinical adoption. Users must inform and ML tools influence healthcare decisions. Moreover, ML should support, not replace clinicians. It's crucial to ensure equitable access to these technologies across the socio-economic backgrounds. As ML becomes more prevalent, maintaining ethical standards and trust with shareholders remains a top priority. Case studies and real world implementations. Several real world applications and research studies have demonstrated the potential of ML in ASD diagnosis. For example, ML tools embedded in mobile apps analyze user responses and behavior to suggest whether a child may need clinical evaluation. Research using brain imaging and AI has yielded over 85% diagnostic accuracy in control studies. Pilot programs in start hospitals have integrated ML models into diagnostic workflows, supporting clinicians with second opinion tools. Now, integrating ML tools in clinical practice. Successfully deploying ML tools in ASD requires Clinical integration. Tools should be user friendly and interpretable for healthcare professionals. Seamless integration with existing EHRs can streamline diagnosis and follow up. Future directions. Future work in ML based AST diagnosis will involve more robust, diverse datasets and explainable AI models. Wearable technologies and mobile apps will collect richer real time behavioral data. Conclusion. Machine learning holds significant promise in transforming AST diagnosis. It enhances speed, accuracy, and scalability of assessments while supporting early intervention. By leveraging data from behavioral, speech, imaging, and genetics, ML models provide nuanced insights into AST indicators. Thank you.